Good afternoon, everyone, from Dunrovin Ranch in Lolo, Montana. I'm delighted to have you back, and I'm very delighted to have Dr. Kerry Forsman back. He was here a couple weeks ago, and we learned a lot from you. And
I hope so.
yeah, and we're anxious to continue, kind of pick up where we left off.
Okay.
And just to remind you where we left off last time is we brought up the species of pika, which is kind of a unique little guy, isn't he?
It is. It's a small lagomorph, a bunny, a small little rabbit, very unique. We've got two species in North America, one in Montana and the east coast or west coast down to California, and very interesting animal that lives at these high elevations.
Well, Dr. Forsman, you did some of your specific research on pika, did you not, for your PhD?
Not for my PhD, no, as an undergraduate.
As an undergraduate.
The very first research I ever did, what got me interested in wildlife biology 50 years ago, almost to the day, I was studying pikas in Glacier National Park, and I'm going to talk a little bit about that. I talked about pikas last time, but I had no pictures to show because it was a question that came up.
Right.
So I'm going to show a few pictures to explain what I mentioned last time and talk just a little bit more about that species before we go on.
Okay. Winter, getting in and out of winter, and now that winter's starting to fade, getting out. I want to remind everyone that Dr. Forsman is the guy who really did write the book on mammals in Montana. This is his second edition, and I encourage you to get it if you're going to be watching our cameras for a very long time. It would be a great reference book. It's got some beautiful photos and just lots of life history information about our mammals. Thank you for doing that. Is it a textbook as well?
I use it for my classes at the university, but it's available online through Barnes & Noble and Amazon.
Good.
So,
well, with that, let's get started.
Okay. The first slide that I show here is Glacier Park. If any of you have been to Glacier National Park, this area that I'm showing here is just down from Logan Pass. So the visitor center at the very top of Logan Pass in Glacier National Park, where the big parking lot is. If just down from Logan Pass is this particular region. It's called Lunch Creek, and it's a big mountain cirque. I'll show you some more pictures here in just a minute. And this is where I actually began studying this pika back in the 1970s, early 1970s. In the winter, there's 30 feet of snow in this area. This is actually the visitor center for Glacier Park at the top there, and they'll get up to 30 feet of snow. The cirque that I worked in is then covered. So these pikas, this tiny little rabbit, which again is about the size of, they're very, very tiny. They live in these boulder fields, okay? They don't hibernate at all. And so they're responsible for storing all of the food that they'll need to get through an entire winter, okay? Maybe 6 or 8 months, usually probably 8 months, where there's no food available for them at all. So they have to store all of the food that they're going to live on. So they build these little pantries for food storage. And these animals are very small. They're incredibly cute.
If you've seen one, you fall in love.
Yeah,
really.
you really will. They're just fun to watch.
Yeah.
They're very interesting. They vocalize a lot, so they'll talk, chirp, and they have lots of different vocalizations to talk with each other or to warn each other about various types of prey or predators, weasels or hawks and owls that might be chasing them. So they're very watchful and very alert, for the predators, and they'll communicate that. They live in these boulder fields, and this is the boulder field in that cirque, Lunch Creek, that I just showed a picture of a minute ago. And for reference, if you look to the middle of the right-hand side, there's a white object there. This is actually a person that was working with me. This picture was taken in 1971, and when we were working on this boulder field. And that was another student that was helping me. So you get the size of this boulder field. They're pretty large boulders and lots of space in there.
I'm going to interrupt you for a moment, Carrie. Those of our viewers who don't live around mountains may not know what a cirque is.
Well, a cirque is just a circular mountain face, okay? Circular area of rock wall at, say, the head of a canyon. So you have these boulder fields up in this closed, enclosed cirque, and it creates kind of its own environment, and it's a unique habitat up there. They call it a cirque because it's circular in shape at the head of a canyon. But you get these boulder fields that are there, and the pikas are living in these boulder fields. And what's interesting is that, as we mentioned last time, these pikas, very tiny mammal, doesn't live in family groups, okay? They live individually. So each individual animal has its own home range, the area that it lives in. The red that I show here might be the portion of the boulder field that one animal has. So this might be a female, and this is her home range. She lives right there. This might be a second pika, okay? The home ranges don't overlap. They have their own homes, just like you and I might have our own home with a fence in between. These animals have their own space, and they don't allow others to come into their home range. And so they partition their boulder field like this. And what's interesting is that, you know, they live in that space, but the food is down at the bottom. You see all the grass down at the bottom of this boulder field. So the pikas have to run down the boulder field every day, maybe 100 times every day. They run down through the boulder field and go to the grass and eat, okay? So during the spring, or actually during the summer, they're under snow in the spring. In the summer, when the snow melts off, they'll start running down to the base of this boulder field and eating grass every day, just normally, for their normal nutrition. Here's an animal that you see. It's kind of camouflaged, and that's important, but it's got a mouthful of grass, so it's just come down there to eat for that particular point in time. But then what it does is it grabs very selective foods. It grabs flowers, not grass, but it grabs flowers, cuts these, and takes these back up into its boulder field. It goes back up, runs back up through the same pathway to its own home range, and stores those flowers into what we call a hay pile. So if you look at these hay piles, you've got large amounts of grass. If you ever have an opportunity to walk onto a boulder field like this, just walk across the boulders and look down, and you'll see big piles of grass. You're trying to figure out, now, how did all this grass become stored there? And that's what these pikas are doing. An individual pika may have 5 or 6 large hay piles, okay, where they just store the food for the following winter. So once the snows start to come, and the boulder field, in this particular boulder field, will have 30 feet of snow, the grass is no longer growing. There's no food available other than what they've stored themselves under the rocks, under the snow. So they can live for 8 months under the snow and access these hay piles for food to live on throughout the winter. And as we said before, they will eat grass during the day. During the summer, they'll to just, food for the day. Your meals will be grass, which is very nutritious when it's fresh. But when regular grass species dry, they lose their nutrients. The quality of the food goes down very quickly. But flowers, certain species of flowers, have really high nutritional content, and that's retained even though those grasses dry out. So they'll look completely dead, which they are, but they'll retain a lot of the nutrients that normal grasses would not retain. So the pikas are very smart about that, and they store flowers, very species of flowers to live on throughout the entire winter.
So do they take the actual flower in addition to the stalk that the flower is
Well,
on?
both the stalk,
And the flower.
Yeah, the stalk and the flower are brought back up, by the thousands. Literally, they will run back and forth with a mouthful of flowers 100 times a day throughout the last couple of months of the summer. So they're making hundreds and hundreds of trips storing food for the winter.
So for those who have never been up to Logan Pass, summer is a really short season.
Summer's a very short season. I'm trying to remember now. I think the pass usually, being able to even drive up to Logan Pass doesn't occur until late June, early July.
Yeah.
Okay, and there's still a lot of snow. I mean, they've cut the path through. They've plowed the snow so that cars can go up to the visitor center in July, but the snow is still on the slopes.
Right.
So it doesn't really melt off until July, sometime in July, and then starts snowing again in September.
Yeah.
So you have maybe 2 months to accumulate all the food that you need to live for the next 8 to 10 months. Wow. It's a very difficult situation.
Wow.
Here's next to the last slide for pikas, and these little X's in their home range are the hay piles. So they'll have several of these, and they can be, again, 3 or 4 or 5 feet across and 2 or 3 feet deep. For a single little animal, tiny little animal, can live in off of that food source. But the other important point to remember is that it's a very harsh environment, and even under the best of conditions, the animals that live here, these pikas that live here, normally have about a 40 or 45% overwinter mortality. So almost half of the animals that are on this boulder field won't make it through a winter because they haven't stored enough food. If the winter lasts a little bit longer, about a week or 2 longer than normal, if you get a spring snowstorm, these animals will run out of food. It's just like running out of a pantry. You have no food to eat, and you can try to come up above the snow, but there's simply no grass growing. So very high overwinter mortality that these animals have just evolved. This is a type of strategy that they've evolved over thousands of years.
So, Carrie, during this era of climate change, we've seen a lot more erratic weather.
Well, we have, and I'll talk about that with a couple of other species here as well this afternoon. We're starting to see, unusually, we're seeing later snowstorms in the fall. In many areas, we're not seeing as much snow accumulated, but quite often we're seeing wetter springs, which means more snow at the higher elevations. So quite often we're getting later snowfalls in the spring conditions when animals should be expecting less snow and warmer temperatures. So quite often we're starting to see a shift, which these animals are having trouble acclimating to. They can't just recognize this global warming event, and part of the reason we're starting to see even higher mortalities with many of these species is because they were expecting, quote unquote, evolutionarily warmer temperatures in the spring and lower snow levels, and all of a sudden, though you may have warmer temperatures, global warming, that causes in these high mountain areas more precipitation, and we'll get snow at the higher elevations. So it's kind of a conundrum where you're actually seeing warmer temperatures but deeper snowfall in the spring.
Right.
And thus no food available.
Right. And let me ask one more question. Those deep snow, that deep snow obviously would insulate the ground where the pikas are. So in some way it provides some shelter from the...
Yeah, it provides a great deal of shelter, 30 feet of snow insulation.
Right.
So it's actually warm under these boulder fields. It's probably 40 degrees.
Yeah.
Okay.
Yeah.
But that doesn't matter if there's no food.
Right.
If you've eaten all of your food and there's no grass growing, it doesn't matter because you're not going to be able to make it through the winter.
Yeah.
So it's, an interesting situation. One of the things that I wanted to talk about today in particular was, how do these animals really know when they should hibernate? I mean, what tells them snow is coming, it's going to get cold in the winter, and you better start hibernating? These animals, have to prepare. If they're like a pika, they've got to be cutting all this grass and or flowers and storing it, okay, and they have to spend a couple of months doing that. It's not like you can just put a pantry down in a day or two. If the snow starts, you've got to spend a long period. And many of the other species that we'll talk about, and we've mentioned last time, marmots and ground squirrels store fat, okay? Rather than try to put food away that they could eat during the winter, they decide to eat the food during the summer and store it as fat. So they have a large source of body fat, and then they hibernate, lower their body temperature, and live off of this stored body fat, okay? But that takes a couple of months to do.
Right.
You just can't, double your body size by laying down that much fat in a couple of days. It takes weeks and weeks to do that. So the question is, how do these animals know, today I better start storing fat because in 2 months I'm going to need it. I'm going to be hibernating. And then the other question is, how do the animals know in the spring if, like this jumping mouse and the ground squirrels, how do they know when they're deep underground system, protected deep under the soil, how do they know that it's warming up above ground and that the grass may start growing again? What tells them that it's now time to come out of hibernation? Because they can't watch the sunlight, they're underground. So I want to talk about a couple of those. One of the best studies that has really addressed this recognition of pending winter and pending spring is this little western jumping mouse. This species is found across Montana, all over Idaho and Washington and Oregon, down into California. So it has a wide distribution and is one of the best hibernating mammals we know. What this little animal will do, it lives in this meadow system. This is in Montana, where my graduate students and I have researched it. It lives in these meadow systems. It primarily eats seeds. Okay, it'll eat grass a little bit during the summer, but seeds have a much higher fatty acid content, unsaturated fatty acids, and so they're better at creating fats, oils that the animal can store as body fat. So they'll shift to eating huge numbers of seeds to convert into body fat. What's interesting is that these animals, they're a little mammal, okay, without the tail. They're called a jumping mouse because they look like a kangaroo. They've got huge hind legs and tiny little front legs. They hop, okay, so they're a jumping mouse like a kangaroo, mini kangaroo. Very, very long tail to support them. But they're very tiny. I mean, the body itself without the tail is maybe 2 inches, 2 to 3 inches in size. So they're really quite a small mammal. They weigh 18 grams. Okay, grams is kind of a hard metric if you're not familiar with that, but they're really quite small. And they will double their body weight, more than double their body weight by laying down fat within the last month or so in late August into early September. So this animal will go from 18 grams to about 36 to 38 grams. So like you and I, doubling our body size by laying down, that much more fat. And then they're going to live on that fat throughout the winter. So they put down a huge amount of fat, but this is in the late fall or late summer and early fall, and they are tracking photoperiod and temperature. So these animals, like the ground squirrels, okay, and the marmots, are being told that winter is coming by recognizing the change in daylight length, the photoperiod, and they see the days getting shorter and shorter. Okay, so there's less and less light each day, okay, by several minutes, and they recognize that as a sign that winter is coming. And that, coupled with colder temperatures, as the temperatures get cooler and cooler in September, those two events trigger hibernation. This animal will reach its maximum body size, maybe 38 grams. It can't lay down any more fat. Even if they tried to keep eating, they couldn't get bigger. They've gotten as big as they possibly can, and they simply go underground. They'll go maybe 2 to 3 feet underground in a burrow system to hibernate. And what's absolutely incredible is that they will hibernate for 10 months out of the year. So for 10 months, this animal is out of sight. He's 3 feet underground, sleeping.
And as you said last week, hibernation is where they really shut down a lot of their systems. I mean, it's not like a tuber; they're asleep.
They're asleep. I mean, their
Yeah.
body temperature is usually about 32 or 33 to 34 degrees.
Right at freezing.
Yeah, freezing. I mean, an ice cube is 32 degrees,
Right.
and these animals are 33 degrees.
Right.
If you had an animal like that, a ground squirrel or a marmot or these animals, if you had them when they were in a burrow system, if you dug them up and found them, it'd be hard as a brick. Okay, I mean their body temperature is just slightly above freezing. Their heart rate is maybe a couple of beats per minute. They breathe, once or twice a minute, and they're totally oblivious to their surroundings. I mean, it's like an incredibly deep sleep. It takes them an hour to wake up. Okay, if you took a ground squirrel out of hibernation, out of a den where they were hibernating, and put them right here on the table in this room temperature of 70 degrees, it would take them over an hour to warm themselves up to where they could stand up. Okay, so they really aren't conscious to the degree that they would be. They can't recognize that you're there, and again, it takes them more than an hour to simply wake up. So these animals are being told to hibernate. I mean, they're tracking environmental light levels and temperature, and that tells them they better start eating now and storing fat and getting ready to. And then they do for 10 months. Okay, I mean, that's an incredible period of time. These animals only are active for 2 months out of the year, every year. They're long-lived because of that. I mean, they're only active for 2 months, so their body isn't, undergoing a lot of activity except for 2 months out of the year. So they're actually a long-lived species, but they're only active for 2 months out of the year.
So what do you mean by long-lived?
Well, some of these, I mean, like the bats are the same way. The bats can live 20 years. A bat
wow.
is 20, 25 years old, a tiny little bat. These animals probably 10 years.
Yeah.
Okay, which is very long-lived for a very small animal like this. Other animals this body size that don't hibernate. I mean, if you're in Southern California and you don't have to hibernate, your lifespan may be a year, maybe 2, if you're lucky. Okay, so being able to hibernate and shut the system down allows you to extend your life 5 or 10-fold.
So let me ask you about an animal like this in terms of reproduction, when you only have 2 months to get all that done.
That's right. Well, that's right. And I was going to mention that with one of the next examples. What's happening is that these animals, there are a lot of body functions that are called endogenous, things that are genetically programmed internally. And so these animals don't necessarily have to track photoperiod or track temperature for some of the internal systems to become active. When these animals are hibernating, the reproductive system is totally inactive, completely inactive at all. But as spring approaches, or actually as summer approaches, because these animals don't even come up above ground until June or July, before they even come up above ground and come out of hibernation, some of their systems, the brain and the reproductive system, start to become activated. Okay, you have to have a brain to control body temperature and to control respiration, and so all of these other functions and the reproductive system have to be activated, and the brain has to start that process. During the winter, when they're hibernating, the brain is shut down and all the other systems are. So to get back to your point, they actually start organizing and activating the reproductive system before they end hibernation, so that the minute they come above ground, they're able to breed. Okay, they're reproductively active, because you can't spend a month, after you've come above ground, trying to get the reproductive system started so that you can then breed, because a month later you're going to be hibernating. And it takes, pregnancy is 30 or 40 days long, and lactation is 30 or 40 days long. So there's a month and a half that's required to produce offspring.
So do those offspring then hibernate with their mother the first year?
They don't hibernate with their mother. I'll show you this,
Okay.
because we'll get to that point here in just a second. We mentioned that they're tracking photoperiod,
Right.
light levels, and are shortening light levels, and cooler temperatures precipitate hibernation. But in the spring, they're deep underground. They're 2 or 3 feet underground in a little burrow system, okay? And their nest chamber may be, 35 to 40 degrees in temperature, because they've got all this insulation of snow and 2 or 3 feet of soil, but it's cold. And they can't see anything,
Right.
because it's dark. So being in a cave system, so they can't track photoperiod. And the question then becomes, how do they know it's spring or summer? They don't even wake up until summer. How do they know that summer's begun after 10 months of hibernating? And what research has shown, and a lot of studies have done, this was actually done in Montana, a lot of research has shown that when the soil temperature reaches 47 degrees around their nest cavity, so when it warms up in the spring and the snow starts to melt off and the soil temperatures start to warm up, okay, that as that heat penetrates down into the soil, when it gets down to their nest chamber and the nest chamber warms up to 47 degrees, these animals wake up out of hibernation. That's the trigger that tells them that summer is here. And if you think about it, if the soil temperature has reached 47 degrees 2 feet underground, that means on the surface it's much warmer and plants have started to grow. So that soil temperature is telling these animals that it's been warm for a while, and grasses are now growing up above ground, and if I go up out of hibernation, I'm going to have food to eat. So the soil temperature is what is really triggering their exit from hibernation. But
So this is a strategy that would be adaptable to things like climate change, because it's triggered by the actual temperature.
It is. But the problem with that is that it can be out of sync with plant cycles. Okay, I mean, just because you have warm temperatures doesn't necessarily mean it's still, everything is still in sync. And the problem is you get caught on the other end. You may come up earlier, and the grasses may start growing earlier, so you wake up earlier. But on the fall side, there tends to be a problem, and you may end up hibernating earlier than you really should. And I'll show you just in the next slide here. It's not as complicated as it looks. It's just soil temperature on the left side and the month on the bottom. And what this simply shows is that at the very bottom line there is the surface temperature. So it's about, in this case, it's about 32 degrees. This is centigrade. So this is about 32 degrees Fahrenheit, okay, 0 centigrade. And as you go deeper into the soil, okay, the soil temperatures are warmer. So the point is, if you're living on the surface, it would be very cold, but if you're living 2 feet underground, it could be 8 to 10 degrees warmer, which would be around 40 degrees Fahrenheit. And you can see throughout the winter, from starting in late September, the temperatures drop very quickly and don't start to rise until June and early July. So this is that 10-month period when these animals are hibernating. And so you've got this block of roughly 10 months where hibernation occurs, but in where this arrow is, the red arrow on the left or right-hand side, in late June, the soil temperatures are starting to warm up to a point where the animals will come above out of hibernation, and this is when the plants start to grow. On the top panel there on the right, you have plant growth, you have flowering, and you have seeds being produced. So these animals don't come out of hibernation until late June. Plants are available so they can start eating grasses to live, and very quickly the plants are flowering and going to seed, and these animals start eating hundreds and hundreds and hundreds of seeds to convert to fat to get ready to hibernate, okay, starting in September. Okay, so they're only out for 2 months, and everything has to occur there. They have to breed, they have to raise babies, and then the babies have to grow up
And get fat.
and store their own fat, okay,
Yeah.
before they're able to hibernate. And that's such a difficult thing to do. The actual overwinter mortality for these animals is really quite high. I mean, the adults, if they make it through their first winter, okay, if they're born in the late summer and are able to grow up and store enough fat in their body to make it through their first winter, then their mortality is only about 25% after that. Okay, again, they're long-lived. But the mortality of juveniles is 40 to 70%. Yeah. So, 70% of these small young that are born in late one summer aren't able to store enough fat to survive their first winter. So it's a very cruel world out there, and
sure
it's a very difficult strategy to develop. We'll look at a couple of other species here because it's interesting. These animals apparently don't wait in their burrow to detect the warming soil temperatures. They may be deep underground. They may be in rock fields where it's not soil that's warming up. They're deep down in the rocks like the pikas are, except they're hibernating. These ground squirrels are hibernating. What's really interesting about many of these species, the marmots, the woodchucks in the east coast, the ground squirrels across California and Washington state across into Montana, these animals are hibernating very deeply underground in their burrow systems until about March. And then in March, it's an endogenous mechanism. Okay, their body evolutionarily is programmed to start to become active. Their brain wakes up, they start to warm up, and what they will do is dig up through the snow. They may dig maybe 3 or 4 or 5 feet of snow, maybe more. They'll dig a hole all the way up through the snow and look around and see, if it's nice out. I mean, and see how deep the snow is and see if any plants are starting to grow, what the temperature is outside. And if it's warm and plants are starting to grow, then they've hit it just right, and they'll stay active and start breeding and come out of hibernation completely. But if it's cold still, and there's still too much snow, and they don't see any plants and flowers starting to grow, they'll go back down into their burrow and hibernate for another week or two. Okay, and then they'll come out again and check. So these animals are programmed. We don't know how, but they're physiologically programmed to come out early and to sense the environment, to check it out for themselves, and make a decision.
Well, that's clearly the origin of Groundhog Day.
Yes.
The groundhog coming up and checking things out. But that's really interesting it's sort of understandable how an animal might be programmed to be asleep for so many months, almost timed. But to be able to go back and re-enter that state and for another shorter period of time, that's kind of a mystery, isn't it?
Well, it is, and it's a lot more complicated than that. We can't, in fact, these animals get into trouble here, but most of these animals, like the ground squirrels, don't actually drop their body temperature down to 33 degrees for 8 months and stay like a frozen ice cube for 8 months and then wake up. What they do is drop their body temperature down for 2 to 3 weeks and then warm up. They don't really wake up, but they warm up. I guess they wake up, but they're still in the burrow system. They warm up and are active for maybe a couple of hours in the burrow. They don't come above ground. They stay down there and they can't eat anything. They haven't stored any food, living off of body fat. But they wake up for a couple of hours and then drop their body temperature back down for another 3 to 4 weeks. And then they wake up for an hour or two and drop their temperature down for another 3 to 4 weeks. And so throughout this entire 8-month period of hibernation, they're actually cycling through hibernation at maybe 4-week intervals, 4 to 5 week intervals. As it gets later into the winter, February, the coldest months, they may stay in hibernation, deep sleep for 6 weeks, and then wake up for an hour or two and drop their body temperature back down. The strategy, it's more complicated than this, but that periodic arousal and then going back into hibernation seems to be linked to kidney function. Okay, your kidneys. I mean, you're alive. You know, even if your body temperature is 33 degrees, you're still alive. Okay, and you still have a heartbeat, and you still are breathing, but very slow. But you're metabolizing those fats, right? You're living off of stored fat. So your metabolism is still occurring. Well, metabolites build up in your body. The waste systems, nitrogenous wastes, build up by burning fats, you know, to keep yourself alive. And those nitrogenous waste, nitrogen builds up in your blood system and your whole function of the kidneys. I mean, our kidneys are set up to excrete those waste products, okay, on a daily basis. So we get rid of these nitrogenous wastes. They build up in the body if the kidneys aren't functioning, and the kidneys aren't functioning when the animal is 33 degrees. So the nitrogenous wastes start to build up, and that's ammonia is a nitrogenous waste. So you start to build up poisonous nitrogen wastes in the body, and you have to get rid of those. The only way to get rid of those is have a functional kidney. So you wake up for a couple of hours, and as you warm up to normal body temperature in your burrow, the kidneys become functional, and you urinate. You excrete those body wastes, and then you can drop back down into hibernation, allow your kidneys to shut down again for another month. And as those wastes build up, you have to wake up to eliminate those body wastes. So, I mean, it's really quite a complicated physiological process, but these animals aren't coming out of the burrow. They're not coming out in the middle of the winter and running around. They're still deep underground, cycling in and out of hibernation. But in the spring, endogenously, they're triggered to recognize that they've been doing this for 8 months, and things should be getting better. So then they wake up and they come up above ground to check things out. So again, if it's fine, they'll stay out of hibernation. But if it's a late spring and you're still getting a lot of snow and nothing's growing, they'll go back down and cycle again for another several weeks.
Very interesting.
Yeah, very interesting,
Very complicated.
but very complicated, and we can see where climate change, warming conditions, will greatly alter this. I mean, we see that in birds' abilities to migrate. They're migrating earlier than they used to, and they're coming back to their nesting grounds when food isn't available up here. So they're recognizing that warmer temperatures in their southern migration areas are telling them that spring is coming, and so they're coming back north, but out of sync with the northern climates now, because the photoperiod has adjusted this and warming temperatures have. So they're actually coming back to their nesting grounds before food is available. And we're seeing huge die-offs of birds because the food that they would normally anticipate being available is not available.
Yeah,
And
climate stability is really an important aspect of
it is, and we're just now recognizing
Right.
how significant many of these problems will be. This is one example, one of the last examples I'll talk about that really demonstrate this. This is a yellow-bellied marmot, okay, beautiful species, one of two that we have in Montana, but this yellow-bellied marmot is the single species that we find in Washington and Idaho and Oregon, California, down through the Sierras. You have this species as well. So it has a very long latitude that this animal ranges over. And this particular species has been studied for many, many years, 40 years or so. A continuous series of studies have been done actually in the Rocky Mountains in Colorado. And what they're showing is that animals are starting to come out of hibernation earlier and earlier and earlier. There's just a couple of graphs here, pretty simple. What you see is the date of first sighting. So people that have been sitting here for 40 years on these boulder fields have been watching all spring, and the minute they see an animal come up above the snow, they record that. Okay, so they've come out of hibernation, they're coming up through the snow and starting to get ready to come out of hibernation completely. And so this is the date of first sighting over, in this case, this was from 1975 to 2000. So this was 25 years of data. We have more now, but this was 25 years of data. And what it simply shows is that the marmots are starting to come out and be seen above snow earlier and earlier and earlier. They used to in 1975. The first sightings of these marmots coming above the snow was in mid to late April, okay, in 1975. But by the year 2000, it's now in early April, and in fact, over the last 20 years, these animals are now coming out in March. So the point is, they're because of temperature changes, because of global warming, these animals are coming out earlier and earlier and earlier than they ever did before. But think about this for a minute. Again, this first sighting, but this is the air temperatures that these animals are responding to. So back in the 70s and early 80s, the animals were not coming out until May, and the temperatures, weren't really warming up until about that point in time. But what we're seeing now is that the temperatures are getting warmer and warmer earlier. So in March, mid-March, we're starting to see temperatures 22, 24 degrees. This is 60, 70 degrees Fahrenheit, and 50 to 60 degrees Fahrenheit. And the point is, these marmots are coming out above ground earlier because the air temperatures are warmer. We talked about before, they're coming up through the snow, sensing, what the air temperatures are. And that's all well and good, but the problem with that is that in these same areas, this is in the Rocky Mountains and high up in Colorado, those same conditions, the warmer temperatures in the spring, air temperatures are actually, because of the mountainous conditions, are creating spring storms. And so quite often we're getting late spring storms, which we didn't have before. So we're seeing snowstorms, late spring snowstorms occurring at these higher elevations. Even though the air temperatures are warmer, that's creating this moisture. And we're seeing snowstorms at the higher elevations, even though the air temperature is warmer. So the marmots are being told to come out earlier because it's nice and warm, but the snow is getting deeper, which means there's no food to eat. And every time they wake up and come up above ground to look for food, they're burning up fat. The minute you warm your body temperature up to 98 or 100 degrees, your metabolism is much higher. Your heart rate is 200 or 300 beats per minute. You're breathing, you're running around, so you're exercising, which means the stored fats that you had are used up very, very quickly. And so it's a mixed message. You're being told to come out earlier because you're tracking air temperatures, but the food isn't available, and you've burned up your fat supplies. So we're starting to see these populations die off because of global warming. They're out of sync. Just like the birds are out of sync migrating back north when the insect populations and the flowers aren't available.
And it's happening over such a short period of time that evolution can't keep up.
For the most part, that's true. Okay, yeah. And we have one last example, but I can't really get into it in a lot of detail. Evolution takes a while, okay, to track these types of events. And the global warming is happening very, very fast. So evolutionarily, these animals aren't able to shift as quickly and recognize that. So it's not to say that they're all going to go extinct, but what we'll see is, some of these individuals, like a normal population, some individuals wake up earlier than others, just naturally, okay? And those that, say, may not wake up quite as early may benefit,
right.
Okay? So a certain percentage of the population is going to lose. There's still going to be some that haven't been as significantly affected. So I'm not saying that these species are going to go extinct quickly, in the next 10 or 20 years, but it's going to be hard for them to adapt to these global changes. And we are already seeing that with the pikas. I mean, the southern pika populations, pikas are distributed into, not deep south, but I mean into Wyoming and Colorado areas. And we're starting to see many of those populations go extinct, okay, because the higher elevations are warming up too much. Pikas being so evolutionarily developed toward these very cold conditions, okay, to a pika, 70 degrees is a death sentence. Okay, I mean 70 degrees is way too hot for them. They can't. If you just took a pika and put it, you know, in an enclosure up in Glacier Park, in an enclosure, and didn't allow them to go under the rocks, when the temperature got to 70 degrees, they die. Okay, you and I might be comfortable at 70 degrees. Pikas, the only reason they're able to survive is that when it gets warm during the day, they go under the rocks. Okay, so if you go to these boulder fields in the middle of the summer, I mean, it's beautiful, but you'll watch the pikas in the morning and in the evening, but during the day, you don't see any. It's because it's too warm, and they go down into their boulder field when it's 40 or 50 degrees, nice and comfortable down there. So what we're starting to see is that with these warming temperatures, the animals aren't able to acclimate to that, and the temperatures are warming up deeper into the boulder fields, and they're simply are going extinct. There's no place for them to go. They can't migrate north, you know, like a larger mammal might be able to walk 50 miles, 100 miles north, or 500 miles. These animals are tiny little animals. They can't migrate like that. And if the tops of the mountains become too hot and they don't get the snows that they used to have, they're simply going to die. And we're already seeing that. We're seeing the extinction of many of these southern populations. The last thing I wanted to talk about, I don't know how we're doing on time here.
We're doing fine.
Okay.
We're going over a little bit, but that's great.
Okay. Well, this is fairly short, just a few slides. But one other strategy that many animals have is to change the coloration of their coat. If you look at this suite of animals here, many of these, the jackrabbits and the mountain hare and the weasel and the long-tailed weasel, all of those species are found here in Montana. They're found in Washington and Oregon and California. Okay, so we see a lot of these species across this part of North America. And then you have the others like the Arctic hare and the Arctic fox are in North America, but further north. And then you've got collared lemmings and Siberian hamsters. These are all over the world, okay? So my point is we've got a huge number of different species, both predators like the foxes and the weasels. Okay, they're carnivores, so they're eating the rabbits and the mice and the hamsters. So you've got both predators and prey species that don't hibernate, they don't migrate, they live where they are, even if the winters become very harsh, okay, and they simply have to accept that fact, and they have to find food in the middle of the winter, even though it's very cold out. What's interesting is that all of these species that I show, and many, many more, change their coat color. I mean, in the summer, you know, you've got grasses and woods and forests. You know, it's a mixed color pattern out there. And if you're a prey species like a jackrabbit or a hare, you have to blend into the environment. I mean, you want to look brown. If the background is forested area and brown, you want to look brown so that the predators can't see you very well. When the snows come, and these animals, as I said, don't hibernate, they don't go underground for the most part. They are foraging every day, running around, okay? But the background is white. You may have 3 or 4 feet of snow. So what these animals do is change their coat color. They become white. Here's a snowshoe hare in Montana during the summer. Beautiful little animal. And brownish in coloration because it lives kind of in the forested habitat. In the winter, it turns white. Okay, so it's completely white, and that's so that it can blend into the background. So in the summer, if a fox is chasing this snowshoe hare, it'll be difficult to see because it's blending into the brown forested habitat. But in the winter, it's nice and white, and so the same fox chasing this snowshoe hare is going to have a hard time finding it because it's turned white. So it's a strategy that has adapted these animals to living in cold winter climates when they can't hide. They can't disappear or go underground for long periods of time. They have to remain active. The best way to do that is to blend in to the background. And this is also regulated by photoperiod and temperature, air temperatures, like hibernation is for many mammals. So what's interesting is that these animals will begin tracking photoperiod. The days get shorter and shorter and shorter going into the fall. They recognize that, and as that shorter day length is coupled with cooler and cooler temperatures, that triggers their brain to change the body chemistry to cause the coloration pattern to molt and go from a dark pattern to a white coloration. Okay, you can do this in the lab. We've done this with weasels, did a lot of research on this, where you can simply take an animal like this, put him in a room. It could be in the middle of the summer, okay, but you put him in a room and you change the light cycle to make them think that it's fall or winter. You just make it short day lengths for a month, and they think that it's winter, and you cool the temperature down in the room, and they'll change to a white color pattern, okay? And it's the middle of the summer. But they're being triggered by photoperiod and temperature changes. But what's really interesting is if you look at these species, and this is the last example, this is a long-tailed weasel. I took this picture on the Beartooth Plateau, which is down near Yellowstone National Park. And this is very high elevation. This was about 11,000 feet. And this is a long-tailed weasel. This is in the summer. This was in July. This one had actually just caught a vole. So it had just been out hunting, and it caught this vole and was taking it back to its nest, probably to a litter that this animal had. But this is its summer coloration pattern, and it blends in. It's kind of yellowish and brownish, and you can see the grasses over on the right-hand side and the mixture of colors in the rocks. From a distance, this animal blends in, okay, and it's hard to see. In the winter, it looks like this, okay? Changes to this white coloration because this is a predator, and it wants to be sneaking up on its prey species. So you want to be the same color as your background, not only if you're a prey species, but if you're a predator, sneaking up on animals. The last slide, what's most interesting is that this is the distribution. The green that you see here across North America and into South America, this is the distribution of this long-tailed weasel. So we have it in Montana, we have it across California, again, all the way down the west coast. It goes all the way over to the east coast from Maine down into Florida. But what's interesting is this same species, okay, the same animal, if you moved it, in the north, it will turn white because it's tracking photoperiod and temperatures. But that very same animal, if you flew it to Florida, it wouldn't change color because the photoperiod at that latitude is longer day lengths, not as short as we have in the north, and the temperatures are warmer. So it's not being told to change color, and it doesn't, and there's no snow. So it retains its coloration pattern that's appropriate for its environment. So we see that, I mean, in California, at the higher elevations, the species would be found. It would be white. But that same species down at the low elevations along the coast during this winter, where there's no snow and it's warmer, would not change color.
Very interesting.
Yeah.
Carrie, you've piqued my interest in a number of things, and I would like to invite you back. I hope you're not going to get tired of me. But one of the things that I'm interested in is how you know these things. And what I'd like to ask you to do some future date is to come with one or two animals and dive into how people figured out the answers to these questions. Mm-hmm. You know, because
sure. That's what we've done. All my graduate students.
Yeah.
You know, and
right.
We do the research.
But you talk about bringing the animal into the lab and changing things. I mean, I think people would be interested in exactly. It requires some field studies, some lab work, and finding out the physiological mechanisms by which an animal changes hair color, fur color because of photo length. I mean,
Right.
there's a physiological.
Well, there is. That's 6 hours of discussion as
Yeah,
well.
okay. Well, we'll parcel it out.
Yeah.
Okay, we'll
Yes.
parcel it out. But
Yeah.
I think that's fascinating, and people who have not been involved in wildlife research, it's really a question. I mean, how do you figure these things out? You get peaked in the field, you see it happening, and you think, okay, now I've got to.
Let me give you one example, and we may come back and elaborate on it. The study I talked about with the jumping mouse,
Yeah.
where I said the soil temperature has to be 47 degrees before
Right.
this animal wakes up.
Right.
The person that was doing that research was actually in Montana, was taking probes, temperature probes, in the field. He was going out, he was finding these burrows where the jumping mice were, and he dug out several so he could see what they looked like. And then he would take a temperature probe and he would place it down in 2 feet underground, okay, and measure soil temperature. So, and he would leave it there, throughout the entire winter and spring. And he would then be able to say at 2 feet underground, where this den system is, the soil temperature is 44 degrees.
Yeah.
And tomorrow it's 45 degrees. And the next day it's 46 degrees. And the minute it hit 47 degrees, all of a sudden these mice were coming up above ground, running around.
Very specific.
Very specific. And then he took that information from the field and went into the lab, caught some mice, brought them into the lab, and kept them in captivity in containers in a room, and then he could change temperatures. And he could put the temperature down to 40 degrees, and these animals would hibernate. Okay, it takes a while. It doesn't happen like flipping a switch on
Right.
your thermostat. It may take several weeks to program these animals, which is done in the field. But these animals, if you program them right, they will go into hibernation in the lab. Okay, and then you can warm the body or the temperature of the cage up half a degree a day. And then when you reach that threshold of 47 degrees, all of a sudden they wake up and they're
Right.
looking around and they're ready to go. So it's a combination of field work with a lot of monitors,
Yeah.
and then taking it back into the lab to fine tune it.
Right. And I'm sure that recent innovations in technology and instruments to be able to
It's
do
been
this.
fantastic.
It's been fantastic,
It's
yeah.
been incredible.
Yeah.
I mean, the technology that we have now
Is-
in tracking animals,
Yeah.
radio collars,
Yeah.
and miniaturizing temperature probes,
Right.
where we can implant them into the body now.
And they can automatically record it.
Right. Yeah. You can sit, in your office and you can watch their body temperature on your computer.
Computer screen. Yeah.
Yeah.
This has been really fascinating, Carrie. I really appreciate your
No, it's been fun.
coming here. As I told you right before we started, I did have some questions from viewers about birds, and specifically about birds' feet. I mean, people will see the geese out on the Bitterroot River ice just sitting there or walking, and that looks pretty cold, and their feet don't stick.
It is cold. Yeah.
They don't stick to the ice. So could you just address
Well,
that
I mean,
for a moment?
both birds and mammals that I work with mostly have a lot of special anatomical features, especially in their feet, that do several things. First, it keeps the feet from being exposed to extremely cold temperatures. I mean, if you look at we even can relate to this, our fingertips, okay, don't have a lot of blood vessels in them. Okay, it's why your fingers, when they get cold, they turn white. Okay, it's because the blood is being concentrated deep down in the body and deep into the fingers, and you don't want blood out into the surface because there's a surface area and you're radiating heat, you're losing heat. Okay, so the body's strategy to keep from losing heat. Remember last time I said when you want to keep from losing heat, you decrease your surface area. Rather than having an arm sticking out like this, if I bring it close to my body, I have less surface area. This whole area isn't exposed to the cold temperatures. So by tucking my arms in, I'm retaining that heat. I'm decreasing surface area. And if you look at birds and you look at mammals, the feet are very, we would say, calloused. Okay, they're very, very many layers of dead skin. I mean, the surface of your skin, like your feet, is dead skin. Okay, and it can thicken, and it's dead. Okay, so you're not supplying blood vessels into the very surface tips of the skin itself. They're kind of calloused. and so you build up this dense, thick layer of dead skin, okay, which is on the surface feet of birds and on mammals. Again, if you have a dog, look at the pads on their feet. Okay, they're very rough. They're not, pink, like blood flowing through them. It's a dense pad, but it's a dead, thick, cornified surface, which, you're putting that against the cold temperatures, and you have no blood vessels there, so you don't feel that cold, and you don't have as sensory a set of nerve systems in those pads. The other interesting thing is in all these species, in birds as well as mammals, if you look at an animal that lives in cold temperatures and has to live, like wolves running around in bitter winter, or swans, sitting on the bitterroot here. They have these very long legs. Okay, one of the things that you'll see is if they're sitting on the ice or something, they'll tuck their body in. They'll tuck their wings down. They'll tuck their feet up against their body again to decrease surface area. If they're standing up, quite often you'll see birds tuck one leg up against their body and stand on one leg, and they'll alternate that. What they're doing is, again, decreasing the surface area of that limb and keeping blood, heat from escaping from the blood vessels. The other really interesting thing is in all of these animals, they have long limbs. Okay, if you look at a wolf, standing there, the leg is very thin. Okay, most of the muscle is up next to the body. You don't have a lot of muscle in these legs. They're very long, thin legs. What you have is tendons running down to control the foot and allow it to run, but the muscle mass is up against the body. The point is, the blood vessels that are going down into the limb, the blood is actually shunted very quickly back into another vein. So you have blood coming down an artery, shunted through special vessels that I don't have, shunted into veins, and the blood comes back into the body very quickly. Only a small amount of blood goes down out along these limbs, and it's concentrated in the center of the leg in birds and in mammals. So the point is, most of the heat in your blood is being retained, brought back into the body very quickly, and only a small amount of blood is going out into the long limb to maintain the life, to keep those tissues alive. But it's centralized in the central core of the leg, so that it's not close to the surface and doesn't radiate heat. So there are a lot of anatomical specializations that birds and mammals have that stay out in the wind and exposed.
This is fascinating.
It's complicated.
It's fascinating. And I really, really appreciate your coming. Mm-hmm. This has just been delightful,
it's been fun.
Dr. Carey, Dr. Forsman. And let's just close by pointing out these bear skulls that we have here on the table. Last week we had just one. Could you
both of these are bears. This, the larger skull here is of an Alaskan brown bear, and it's really quite large. So this is a brown bear or a grizzly bear. This would be a little bit smaller in Montana, but a very large skull. And the one over on my right, your left, I guess, is a black bear. So we have two species here in Montana. The normal size of a black bear in Montana, maybe, a good sized black bear, maybe 200, 250 pounds. They can actually be larger in some areas. In Pennsylvania, they may be larger, and it has to do with food resources, food availability. But a good sized black bear may be 200, 250 pounds. A grizzly bear in Montana, a good-sized grizzly bear may be 300 pounds, 400 pounds. They get much bigger. I mean, we've had some that are 600 or 800 pounds here, but for the most part, they're 300 or 400 pounds in size. Up in Alaska, especially along the coast, where the animals are eating a very rich protein diet like salmon, they can be very large. They can be well over 1,000 pounds, a coastal bear. But the same species, the same species of brown bear or grizzly bear, if it's on the coast, it can be really quite large because of that food supply. But as you go inland, okay, into, say, the Yukon, British Columbia. You go away from those salmon resources and get more into berries and ground squirrels. The body size is much smaller. So, it's really a function of food resources and genetics.
Yeah, it's a striking difference.
Oh, it is, yes. And they're very different species.
Yeah. Well, Carrie, thanks again, and I'm going to have you back if you're willing to come.
Sure.
We've
Yeah.
really enjoyed you.
It's fun.
Really appreciate it. And with that, we'll say good afternoon, and thank you for joining us. And do come back on Thursday. We have a little surprise if the snow stays. So there's a hint. Thursday at 2:30. Okay. Thank you all, and goodbye.